energy and sustainability. We're pleased to have Cynthia Lo, the Walter E. Brown Career Development Assistant Professor of Environmental Engineering, as our speaker. Cynthia is the Principal Investigator for the Computational Activated Materials Lab, and she's also Principal Investigator and Seminar Chair for PARC. Cynthia has undergraduate degrees in Chemical Engineering and Chemistry from the University of California, Berkeley, a master's degree in Chemical Engineering Practice, and PhD in Chemical Engineering are both from MIT. Professor Lo came to WashU in 2007 from NIST, which is the National Institute of Standards and Technology, where she was a postdoc. In her research, Cynthia uses electronic structure calculations and molecular dynamic simulations to study the structure and reactivity of molecular and nanoscale systems for solar energy utilization, which is what she'll be speaking about today. We look forward to hearing more about solar energy. Thank you.
Thanks, Natalie, for the introduction, and thank you all for coming here. Today, what I thought I would do is give a little bit of an overview on solar energy, maybe some of the things you might not have learned in classes before, but I know a lot of you are interested in solar energy and might have been wondering how do you actually tie in your engineering knowledge from your classes into actually designing solar cells. So I wanted to give a little bit of the theory of that, and then also talk about some of the projects in my own group, which I think tie in pretty well with solar energy utilization. So first, I just probably want to just remind you again, but probably don't need to remind this audience, is that basically, most of the energy portfolio that's used in the U.S. today and also in the world, which is pretty similar, most of the energy is coming from non-renewables. Petroleum, natural gas, and coal. These are what we call non-renewables, and the majority of our energy portfolio is made of these resources. Renewable energy in the form of hydropower, biofuels, wood, wind, solar, geothermal, makes up only about 8% of this energy portfolio. And so, you imagine that as our energy needs grow, we would probably need to invest more in these renewable energy sources. But right now, the amount that's being used is very small, and you see solar is probably less than 1% right now. And this is just a plot I made from some of the data from the U.S. Energy Administration, Information Administration. And you can see here that our current energy consumption worldwide is about 14 terawatts per year. And so you see it's probably projected to increase over the next 20 or 30 years. It's going to increase pretty much linearly. And so this is our current needs, but you can see our projected needs are going to keep increasing, which is why I think we should try to invest more in these renewable sources of energy. You might argue that, well, of course we need energy, electricity. Countries as they've been developing have been using an increasingly larger proportion of electricity and energy. There was a talk with last year, I think, at the McGee Symposium last year in October, where one of the speakers argued that China is doing really well because now they're burning more coal power, so they're making more electricity, so that's why people are doing better financially. Okay, so you might argue that, well, maybe you might not need to use coal power per se, but you do need to generate electricity. A very vibrant economy does depend on having abundant sources of electricity. And you can see from this graphic Human Development Index versus the annual per capita electricity use, Western countries such as the U.S. and Canada, use a lot of electricity per person. China and India are slowly coming up in this curve, but you can imagine that as countries develop socioeconomically and government, you'll imagine that they'll need even more electricity. And so I would argue that only solar power has the potential to actually satisfy our global energy needs. So currently I would say it makes a part of a portfolio of energy uses, but it's fascinating to think about the prospects of solar energy, and that if you think about the amount of energy that reaches the Earth, 174 terawatts of radiation reach the Earth. If you think about how much we actually need right now, which is 14 terawatts, you realize that there's a lot more than we actually need, which is great. Even if we account for all the radiation that's reflected off of the Earth from various processes, absorbed by clouds, etc., we still get on land about 51% of that, which calculates out to about 89 terawatts. And so because more solar energy reaches the Earth than is actually needed for all of our energy uses yearly, I would say that this is the only technology that actually has the potential to completely satisfy all of our needs. Whether it ultimately will do so is another story, but this is the only technology currently that will actually work. Wind, geothermal, none of those will actually have the capacity to fully satisfy all of our current projected needs. So now what I'm going to do is talk a little bit about photovoltaics, which I think are probably the most commonly studied technology for solar energy utilization. Talk about conventional silicon-based technologies that you've heard of. Also talk about some of the emerging technologies that we're working on in the PARC Center. All right, so this is a pretty familiar picture. If you didn't realize, this is actually Brower Hall. So you probably recognize some of the pink buildings that you see kind of around the corner, but this is actually Brower Hall. So this guy is installing the solar panels. This is one of the investments that we made in this building to actually make it LEED certified and actually so that we can actually generate much of the electricity that we actually need. So these are some solar panels on the roof of Brower. Another famous picture you might have seen where this is a solar farm in Colorado. And so you can see all these solar panels are all put at different angles to try to capture as much sunlight as possible. One thing you might not know is that these panels actually were not manufactured in the US. They're all manufactured in China. Okay? And so let me just show you the headquarters of this plant. This is Suntech, which is in Wuxi, China, which is near Shanghai. And so this is actually their facility, and so they actually have one of the walls completely covered with solar panels, which is actually pretty impressive. Okay? And so yeah, so they basically generate all the electricity they need. They have smart windows, etc. And you might wonder, so how do they make so many solar panels that they can actually put it on pretty much one side of their building, on their headquarters? Okay. So it's not surprising, okay, that they're able, that in China, Suntech and other manufacturers have been able to lower the cost of solar panels to about $128 per watt. Okay? And what we would call the holy grail is about $1 per watt. Okay? If you look at all these technologies, you see how far behind the U.S. is and Europe is. They're about on the high $1 to $2 per watt. Okay? I'll talk about the blue line in just a moment. But you see all these silicon technologies. The Chinese are way ahead of us in terms of being able to lower the cost per watt for these solar panels. And that's why it's not a surprise that China has really a majority of the solar market share. Globally, in terms of making solar panels. Okay. You might be wondering, well, this is a little blue line down there that is using cadmium telluride. Looks like it's pretty cheap, $1.08 per watt. Why are we using that? Well, there's one word to describe this, and that's basically Solyndra. If you think about that, Solyndra also uses this cat telluride technology, and we're making these sort of cylindrical solar cells, also made of cat telluride. And related materials. And the problem with these materials, cat telluride, SIGs, etc., is that they're very hard to manufacture on a very large scale. Okay, so even though they may be a lot cheaper, they have pretty decent efficiencies, almost approaching about 20%. It's actually very hard to manufacture them on a large scale. So for now, I would say that these cat telluride and other technologies are probably not quite viable yet for large scale manufacturing. So even though you can see about $1 per watt there, it's not really commercially viable on a large scale yet. So silicon is still where it's going to be for a little while. Okay. Just want to also just give you a little bit of an overview of how solar cells actually work. Usually you won't see this in your basic thermal classes or physics classes. I just want to give you an overview of basically how things work in a solar cell. Okay, so if you look at here. You see, basically, we have a semiconductor. So basically, silicon's a semiconductor. Lots of compounds: germanium, gallium arsenide, etc. These are semiconductors. And what I mean by a semiconductor is that it has two sets of bands. There's a conduction band and a valence band. And so, those of you who are chemists, probably don't think in terms of bands, but you might think in terms of orbitals. So one thing you might say that these are basically your occupied orbitals, and these are unoccupied orbitals. Okay, so basically, this over here. This is the top of the valence band. It'll be the same as the HOMO, highest occupied molecular orbital. This band down here, the bottom of the conduction band, will be the same as the LUMO. Okay, so basically this is how you can translate your chemistry concepts into physics concepts here. And so basically we just imagine that there's a whole bunch of electrons right here, and there's a big chasm between where the electrons are and where they like to go. And so how they actually are able to cross this chasm or cross this bridge essentially is to have enough energy to be able to jump up from this level to another level. And how do they actually have enough energy to do so? this is where solar energy comes in. Okay, so basically what would happen is that the electrons are here, they're pretty happy here in the ground state. Incident photon from sunlight comes in, and if this photon has enough energy associated with it, so you imagine all of your typical equation of energy being related to hc over lambda, where h is Planck's constant, c is the speed of light, divided by lambda, which is your wavelength. So you can sort of think about which wavelengths of light might actually be suitable for this device. So a photon will come in and it'll basically give an electron in this valence band enough energy to jump up into the conduction band. Okay, so this is where sunlight is really important. You want to have sunlight that's incident on your solar cell so that your electrons will jump up to this higher energy level. What happens is that you end up with an electron here in the conduction band. You have a hole that's left behind. So basically just where the electron was. So basically leave this hole behind. You now have what we call a electron hole pair separation. Okay, so electron hole separation here. And this is what happens is that the electrons in the hole can just move to different sides. So electrons will kind of go in this direction, holes will go in this direction. They basically move in opposite sides. If you see this is a kind of a real thin film solar cell, basically they end up being collected by these lines that are on the top here. So this is what's called front contact. You see these little black lines that are on the front contact. This is what actually collects these electrons in holes and ultimately generates electrical current. That's the basis of how a solar cell works. But it all starts with the sunlight that's irradiating onto the solar cell. Okay, so you might wonder, how do we actually get that diagram with the conduction band, the valence band? So everything for us actually comes back down to what we call the Schrodinger equation. Okay, so this is the basic quantum mechanical equation that's used to solve for electronic energies. So anytime you want to know what electrons are doing, solve the Schrodinger equation. Okay, and so basically it looks kind of complicated, it has this funny symbol, but essentially you can think about this as an eigenvalue problem. Okay, so H would be like a matrix, so it would be an operator, so it would be like a square matrix. Psi is just an eigenvector, so you just imagine a column vector. So you have a square matrix, column vector, compatible sizes that you multiply them together. E is just a scalar, and then basically just have your eigenvector map. Okay, so this is just a simple eigenvalue problem. In the simple form, you can just write this Hamiltonian, okay, which is basically again is your square matrix. It is basically an energy operator. So it just contains basically all of your energy terms. So the basic level, you would say, oh, that's kinetic energy and potential energy. And that's essentially, in quantum mechanics, you just write your kinetic energy in this form, just del squared. And then your potential energy is just V. And this E is the same E that you already see here. So basically, we just get this expression. This is actually fairly easy to solve, even though it doesn't look that way, but you can actually solve it pretty readily. And as I said, Hamiltonian, wave function, and energy. This is what we really want. We actually really want energies. All these equations basically ultimately get us to the energies, which basically show what the electrons are doing, where they are, and how much energy they have. Okay. So if you go back to this plot here, what we end up doing is we solve for these energies, and we basically plot them as a function of the momentum of the crystalline semiconductor. So basically, this is energy as a function of the crystal's momentum. Okay. And then we can also figure out, well, how many is my valence band filled? Do I have anything in the conduction band? And you can do this by solving this Fermi distribution, which is shown here. So Fermi distribution depends on temperature T. It also depends on the energy E. So basically what you want to do is you might want to figure out the conduction band. Okay, so if I'm in the conduction band, what probability do I have to be filled versus not filled? And you basically would calculate this Fermi distribution function, look at the energy of each of these states compared to the energy of this gap right here, and basically just divide by temperature. Essentially, you get this distribution function. What does this mean in practice? This means at t equals 0, okay, e to the 1 over 0 is like infinity, which means 1 over infinity is like 0. So that means at t equals 0, zero temperature, your valence band is filled, your conduction band is completely empty. 0 probability of having anything up here. However, as your temperature increases, or as you get, as your electrons get excited, there's a finite probability that electrons will be excited from the valence band to the conduction band at temperatures higher than 0 Kelvin. And that's all this equation really means. Okay, so what does this mean in terms of the efficiency of a solar cell? So you might have heard these terms, bending around like 31%, 48%. How does it actually happen? Well, you can calculate the efficiency, eta, of a solar cell as a function of its band gap. Okay? basically is just equal to this interval of over the Fermi distribution function, which I showed you before. So this time I put it in terms of lambda instead of E, but you can relate them back together. E equals h sigma lambda. And then it's just basically equal to the band gap of the semiconductor divided by the incident power, and also that divided by the cross-sectional area. Okay, so you can actually calculate the efficiency of a solar cell, and you realize that for a band gap of 1.1 eV, such as is found in crystalline silicon, your efficiency is about 48%. That's where you get this number that you might have heard about, that the theoretical limit for the efficiency is about 48% for these silicon solar cells. This is the equation that you usually get it. And you can actually plot this as a function of band gap, and you can just figure out like how efficient different solar cells are going to be as a function of incident radiation. All right. So that still doesn't explain why Suntech in China is so efficient at making solar cells, and why they make them and why they work really well. Okay. So let me just go back to the picture of the solar cell as you see here. Remember these silver lines that are on the front contact here. Okay. It actually turns out these silver lines are actually very important in controlling the charge collection, so collecting the electrons in the holes in the system. And what happens is that if you have a lot of little lines that are really, really close together, okay, they're really close to each other, they're able to more efficiently collect the charge. Okay? And so it would be great if you can have like a lot of little lines that are right next to each other, very close together, you can have a really efficient solar cell. However, if the lines are too thick, okay, then basically they'll be less efficient at absorbing light because there'll be less exposed silicon out there to actually collect those incident photons. So you want them to be close, but you don't want them to be too thick. So it's a little bit of a conundrum in terms of how do you actually control this process from a manufacturing standpoint. And the conventional techniques that have been used in the US were these conventional screen printing techniques, okay, that we're not able to print the lines any thinner than about 120 microns wide. Okay, so you might be thinking, okay, so what is that exactly in terms of width? Okay, so if you look at your own hair, okay, if you're blonde or redheaded, okay, the thickness of your hair is about 50 microns, okay, about 20 to 50 microns. If you have sort of dark brown or black hair, the thickness of your hair is probably about 50 to about 200 microns. Okay, so that's kind of the thickness we're thinking about here, okay, about the width of a human hair, depending on which color you have essentially. Okay? So this is what's happening. Okay? So conventional screen printing cannot print it any closer than about the thickness of a dark hair. Okay? So that was a limitation, and Suntech was able to overcome that. Okay? So now they're able to make your lines just 20 microns wide. And what they do is they actually use a chemical treatment process where they basically essentially etch it, etch these little lines out, and then basically these etched lines are able to attract the silver. So they're able to just etch them really, really close together, and then silver just deposits on them. So it's not a screen printing, it's like an etching technique. And because they don't need to do screen printing, they don't need to like press on the wafer that as hard, so they actually don't need to have as thick a silicon wafer as you would normally need for the conventional process. Okay, so they can use thinner wafers, they can print the lines closer, great manufacturing process. Every percent improvement in efficiency can cut your cost by over 6%. Okay, so you can improve it just by a little bit, you can actually cut your cost, and that is why China and Suntech and other companies are able to produce these solar panels so efficient, so inexpensively. It's not just because the Chinese people are willing to work for less, or because the government is subsidizing them. These things are also true. But I would say the most important improvement in technology they made was to use this etching technique. Okay. So that's great. So basically these silicon technologies are really improving in cost and efficiency here. So these are the dark blue lines you're seeing here. These are just normal silicon technologies, Suntech, et cetera. Are in this blue region, and so you can see they've kind of down to 20%. If you kind of put multiples of silicon solar cells together, you get into these higher efficiencies, approaching the theoretical limit of 48% here. Maybe just for some context, some companies you've heard of, MEMC, which is in St. Peter's, they work on polycrystalline silicon solar cells, so that's kind of in the this upper end of this blue level here. Amorphous silicon, that's something you might have heard about, so not crystalline, but amorphous silicon. They're able to do like different layers of silicon. So it's kind of putting like different amorphous layers, or maybe amorphous and crystalline together. This is something that's being done by DuPont Apollo in China. That's essentially a multi-junction, amorphous, et cetera, thin film technology. So the efficiencies for amorphous are maybe about 9 to 10%, but they're really cheap, okay? Because you don't have to have purely crystalline silica, so they're kind of down here in the green region. Again, these thin film technologies, so Cylindra, et cetera, also this green region here. Okay, so what about this red region, the red or orange region down here, right at the bottom, has a pretty low efficiency, okay? But people seem to be working on it a lot in the past few years. What's going on there? Well, these are sort of a class of what we call emerging photovoltaics, and they essentially use technologies that are borrowed from nature. And this is, in some ways, one of the themes of now is to get some inspiration from nature and to combine them with semiconductor technologies. So one of the ones you've seen the most is probably this dye-sensitized solar cell, popularized by Michael Gretzel about 20 years ago now, and just won a Millennium Technology Prize for this. Essentially what happens is that you have pretty cheap semiconductors. So compared to silicon, titanium dioxide is really cheap. You basically see it everywhere. You see it in paint, you see it on your donuts, you see it in your toothpaste, it's just a white pigment. Okay, so normally if you think about it, silicon is black, it absorbs all visible light, has a band gap of 1.1 eV. Titanium dioxide, wide band gap, white color, doesn't absorb any visible light, band gap of 3.2 eV. Normally you would think it was a horrible semiconductor, doesn't absorb any visible light, why use it? However, if you combine it with these visible light absorbing dye molecules, what essentially happens is that the dye molecules themselves are the ones that get excited. So basically, instead of the semiconductor electrons getting excited from the valence band to the conduction band, here you have essentially same molecules excited from the HOMO level to the LUMO level, and then the excited electrons from the dye are then injected directly into the conduction band of the semiconductor. So essentially, it doesn't matter what your semiconductor band gap is. You just need the HOMO-LUMO gap of your molecules to be suitable for the incident radiation that you have. Okay, so this is one technology that's showing a lot of promise. Of course, not commercial yet, but people are really interested in this because it's so cheap. Titanium dioxide is really cheap. This is a picture that Bob and his coworkers actually put out just in Science this past summer. And here, they actually looked at the differences between photosynthetic light harvesting, basically excitation from a ground state to an excited state, and how it would work in a crystalline semiconductor. And then when we look at this, it's actually kind of the same concept. Okay, again, you always want to excite something from the ground state to an excited state. Okay, so same thing happens from the valence band to the conduction band. And in the semiconductor that we already know about, we know that if somehow your incident photon gets you just over this bridge to the conduction band, then you're pretty efficient and you can you're pretty happy here. However, if you decide it to be too high, what ends up happening is that you actually lose a lot of this energy to heat. Okay? So that's where some of the inefficiencies lie, is that when you actually have your electrons are actually too excited, and they actually end up having to decay back down to the first excited state. This is where a lot of your inefficiencies are. And if you look at this, these photosynthetic pigments that exist in nature, in plants, and algae, and bacteria, etc., they've actually been well-tuned to absorb light and transmit it efficiency within these light harvesting complexes. And so, I would argue that a lot of semiconductor development could stand to look at photosynthetic pigments for some inspiration in terms of how can you actually make these more efficient. How can you perhaps have a cascade of different semiconductors or a cascade of different molecules that absorb at different wavelengths, than just that are well tuned to the incident light that you actually have available for your system. So a wide array of these pigments actually exist in nature. This is your incident solar spectrum shown here in yellow. And then I just showed a few pigments that we actually work on in our group. So pyridinin here is all the way over in the sort of the blue-violet region here. In the compounds that contain pyridin, they also contain chlorophyll A. So sometimes a pyridin molecule will absorb light and then transfer it to a waiting chlorophyll A molecule, and so it'll downshift this radiation out onto chlorophyll A. Phycoerythrobilin and phycocyanidin exist in these algae complexes. And so our speaker this morning, Madir, actually works a lot on these phycobilosome pigments. Bacterial chlorophyll A is actually pretty popular now. in sulfur bacteria, especially green sulfur bacteria. That's got a lot of interest from the photosynthetic community, and that's all the way out here in this infrared region. So you see most of the pigments utilize visible light. Just depending on where they are they, on land? Are they basically, on the top of like an ocean? Where are they? They'll just basically use whatever light, they have. Okay? The same thing with organisms that live in the bottom of volcanoes or the bottom of oceans. They probably won't get tons of visible light, but they might have lots of heat, and that's where this infrared will come in. So they've all pretty much adapted to where they are and what kind of light they actually have available, and use that. So this is one of the complexes we've been working on, and so we're trying to figure out how to calculate the efficiency of this photosynthetic complex. We know it's going to be high, but exactly how high is it? And if we can understand how these complexes work, then we can hopefully translate these concepts over to solar cells by perhaps either integrating these complexes with different types of solar cells, silicon, or maybe even like quantum dots, etc. Or maybe we can get some inspiration from these biocomplexes and make artificial pigments that work just as well. So this is one that we've been working on quite a bit in our lab. It's called the pyridinin chlorophyll protein complex. This is in dinoflagellates, so algae. And you can see here, this is the gray is actually a protein scaffold that surrounds it. I know it looks like a bunch of cylinders, but it's really a protein. And there's a bunch of little pigments that are inside it. So when you take the protein part away, you actually see these pigments here. You see these red ones that are really long. You see the little blue ones that are kind of more compact. The long red ones are called pyridinins, they're carotenoids, and the blue ones are chlorophylls. So same chlorophyll you've already seen in plants before. Okay, so this is a complex that contains two types of pigments. And so why we're interested is because we want to calculate energy transfer pathways for this complex. Okay, so what you see here, you basically have your electron here in the ground state of pyridinin is excited up to this second excited state, so S2, so not S1. So S0 to S1 is a forbidden transition. If you go from S0 to S2, it is allowed. And then what happens is that there's actually two possible pathways. One is that the system can decay from S2 to the QX band of chlorophyll A. Another possibility is that it can actually decay from S2 back to S1. Okay, so remember, S0 to S1 is forbidden, but S0 to S2 to S1 is actually allowed. So there's quantum mechanical rules, selection rules. And then what can happen is S1 can actually decay over to the QY band of chlorophyll A. Okay, so this has been shown, experimentally that it actually works this way. Exactly what the efficiencies are is still a matter of debate, but what we want to do is to see if we can actually calculate these transition times and also the efficiencies of the transitions to see if we can approach these 100% efficiencies that we've been reading about in the literature. Okay, so we basically looked at these two transitions, S2 to QX and S1 to QY. We looked at these two transitions and tried to calculate these reaction rates. So the master equation we use here is this essentially an energy transfer rate here, and this is an efficiency. So going back to our efficiencies of our system, before I told you the efficiency of a photovoltaic, now we go to an efficiency of photosynthesis. Essentially, this efficiency of the energy transfer process really just depends on the distance between your donor molecule and your receptor molecule, and then this other factor here, which is actually pretty big and complicated. But it has something to do with these terms up here. So this is the rate of the energy transfer, 2 pi over h bar, just a normalization constant. This VDA is what we call electronic vibrational interaction energy. Okay, so we can actually calculate this if we know where our pigments are in the system. So we know our donor, pyridinin, or receptor, chlorophyll, and we basically look to see basically how far apart are they, how are they oriented relative to each other. We can calculate this interaction energy between them. The last thing we also want to calculate is JDA, and that essentially is the overlap in the absorption and the emission spectrum. So essentially your donor will be emitting energy, your receptor will be absorbing energy, so we just want to look at how well they overlap with each other. And both of these terms you can put in, and you can calculate this rate of the energy transfer process in there. And what we essentially want to do is calculate this rate and calculate this efficiency. And we know that experimentally people have seen efficiency up to about 99% or almost 100% for these. But we want to know, with simple calculations, can we actually get these types of efficiencies? So here's just a quick snapshot of our calculations here. You can see for this S1 to QY transfer, you can see actually our energies are pretty poor actually. Our transition times are much longer than what happened in real life, and our efficiencies are correspondingly pretty bad as well. However, for this S2 to QS transition, actually our numbers are actually pretty good. So our transition times are close to what is shown experimentally. Our efficiencies are close to experiment. And so I would say that obviously there's a lot to be done in terms of making improvements to the quantum model, maybe including different types of transitions. Basically instead of just having a point dipole, maybe including different like full vectors, etc., more monopoles, etc. But I would say, like, even just for a quick and dirty calculation that we're able to do, are close to predicting what is actually experimentally observed. And so what we hope to do is that if we can sort of develop these models further and get a little bit closer to experiment, then what we can do is eventually extend these two systems that have never been studied before experimentally and calculate rates and efficiencies of this energy transfer process and guide our development of these sort of emerging photovoltaic cells. Okay. So now I'm going to talk about two different types of technologies that maybe have not gotten as much press in the literature, but are still, I think, sort of viable ways of utilizing solar energy. So the first one I'll talk about is solar thermoelectrics, and the last one I'll talk about is chemicals and fuels productions. And so here, if you look at this solar spectrum again here, basically how much energy is hitting the Earth versus the wavelength of light. See that the amount that can be used by conventional photovoltaics, such as silicon, is about 58% of the available radiation, leaving about 42% that traditionally has not been really used in silicon solar cells. Okay, and this is what we call thermoelectric region. And again, mostly these IR parts of the spectrum. And where I see this that could be really useful is really in terms of like solar heating and also possibly in terms of making electricity. So using this radiation region that mostly has not been tapped into, but possibly either for water heating or for electricity production. So one of the most common ones we've seen here is a solar concentrator. Where these thermoelectrics and other associated materials are used to concentrate sunlight into a very, very small area that then can be used to generate electricity, heat up water, etc. And so, basically, since we took a bunch of undergrads to Hong Kong and China, this past summer we had to show a picture again from China. So you see all these little tubes that shoot off of everybody's roof. Okay, so you see these tubes. These are actually solar water heaters, so basically included various solar thermal materials. And basically they're again, essentially solar concentrators. They basically absorb as much solar energy as possible, try to funnel it down to a small area that can be used to heat water, hopefully eventually also to be used to make electricity. So this is actually pretty common in Asia right now. This is a manufacturing plant where they make them. So how do thermoelectrics actually work? Okay, so basically this is a really neat process. It's actually fully reversible. So the application which we care about is essentially creating a thermal gradient. So basically you have a cold side, maybe this is our room temperature. Essentially you put a heat source at a high temperature. You have this material where you have a cooler side and you basically impose a thermal gradient on the system. Okay, so what happens is that your electrons at the top are like, wow, it's really hot up here. I should probably diffuse to where we actually need heat, which is the cool side. So basically you have electrons that are diffusing from the heat source to the cool side. Okay. Meanwhile, essentially what you end up with is a voltage. Basically, you have all the electrons that are going from the hot side to the cold side. You have all the electrons moving in this direction, creating a current, and creating a voltage as well. So this is how you actually make electricity from this thermoelectric effect. What you can also do is you can also reverse this, and instead of making electricity, you can impose a voltage on the system, and you can actually use this for solid-state refrigeration as well. So you can actually, it's a fully reversible process. So either you can impose a thermal gradient to get electricity, or you impose a voltage gradient to get cooling, essentially. Okay. And so, as an engineer, I always love tying this back into thermodynamics. And so what we assume is that this thermoelectric effect is fully reversible under isothermal conditions. And then we can calculate something called the Seebeck coefficient, which is the absolute thermodynamic power. And the reason why this is actually neat is because this thermoelectric power is actually proportional to the partial molar entropy of electrons. So have you ever wondered, like, what are the electrons doing? How many states can they actually occupy. This is actually proportional to the Seebeck coefficient. Okay? And so this is actually a kind of a neat way where you can actually relate your electrons moving and diffusing to thermodynamic concepts here. And more importantly, we can actually calculate a figure of merit that's related to the efficiency of this thermoelectric. So again, we talk about efficiency of photovoltaics, of photosynthesis, now thermoelectrics. You can actually, for the ZT value, which is the figure of merit, you can actually figure out the efficiency compared to the Cardinal efficiency. You can plot that here. But this is actually a pretty easy thing to calculate, in theory. I mean, it's a little bit complicated, but the terms are pretty easy. You have the Seebeck coefficient, which you already know about, which is proportional to the entropy. You have this electrical conductivity here, and you just basically divide it by the thermal conductivity. Okay, so you look at this term. On the top, you have electrical terms, electrical conductivity type terms, electrical power. On the bottom, you have thermal conductivity terms, so thermal terms here. Okay. And so if you wanted to make ZT as high as possible, what you would want is you want your numerator to be as big as possible, or your denominator to be as small as possible. Essentially, you can control this ratio by tuning the material's impurities, imperfections, and various structural properties in the system. Okay, so you want high electrical conductivity, low thermal conductivity. There. And so what we essentially want is something called a phonon glass electron crystal system. Okay, so basically you want your phonons, which are like vibrations, you want them to basically see the system as a glass. So they can say, oh, it's a glass, it's not really thermally conductive. So basically you want your vibrations to say, oh, I'm not really thermally conductive, I'm going to slow down and not conduct heat as much. However, you want your electrons to see it as a crystal. You want them to say, oh, I think this is a great material, I want to basically have lots of electricity here, and basically want high electrical conductivity, low thermal conductivity. Okay, and so basically these spherulite materials, I know they have a funny name, but they're essentially these K structures. They include basically cobalt atoms, rhodium or iridium, and some of its lattice and then arsenic, antimonite or phosphide and its other lattice sites. Okay? And these K structures actually work out really well for these thermoelectric materials. Okay, and the really neat thing about it is that you can put actually different filler atoms in there, which serve as little speed bumps. Okay, so why there's little speed bumps? You put a big atom in there. So big atom, I would say, like lanthanum would be a big atom. So once you have a big lanthanum atom here in the hole, if a phonon comes in, a little vibrational thing comes in here and hits this lanthanum atom, it slows down. And this is what slows down the thermal conductivity, which is good, which is what's what you want to lower. So basically I'm putting little speed bump atoms in there, lanthanum or barium or whatnot. You can actually lower the thermal conductivity and hopefully not affect your electrical conductivity too much. Okay, so this is what these materials are doing. Let me just show you a sample of what my students have been doing. Instead of doing lanthanum, they've been doing silver and gold, so they've just been putting them into like different lattice sites here, and so it's just one of our just an example of where we're actually filling this. And so these are some of the results that she has compared to the unfilled, which is like the empty spherulite, which is in black. If you look at the red one, okay, which is like just sort of 12.5% filled, you can see that for this gold system and for some of these lanthanum systems, you can actually see that at high temperatures, you actually see that the fillers actually do increase this power factor by a little bit compared to the unfilled system. So this gold one is actually really good. This little red line is above the black line for high temperatures, which is what we want. Some of these other ones are pretty bad, where the unfilled is much better than the filled one. But this one is actually pretty good. And I would argue that this one and this one's okay too, but this one's actually pretty good for lanthanum filled. Okay. So again, this 12.5% filled actually gives you a slight increase in this power factor compared to the unfilled spherulite right here. Okay. And why is this actually useful? Well, it's really useful in case you're making a device. If you want a PN junction there, where you basically have electrons that hold the same material, essentially what you would want to do is just maybe make a cobalt antimonite nanowire or whatnot. You would just dope maybe one half with gold and dope the other half with lanthanum. Essentially, what we see for the gold is that your Seebeck coefficient is actually negative. It's actually less than 0. This is 0 right here. So it's actually all negative. But for lanthanum, this is actually 50 over here. You can see it's actually always positive. So for lanthanum, Seebeck coefficient is positive. For gold, it's negative. So you have a perfect p-n junction, just by doping and alternating, you can just dope one side with gold to make n-type, and then you dope the other side with lanthanum to make p-type. And so you have a perfect p-n junction, little lattice mismatch, and actually a really, I think a really promising material for making these solar thermoelectric devices. And so the last thing I'm going to do is just going to bring it all back together, bring it back to plants and photosynthesis, and you know, show one of the last projects we're doing in terms of you know, reducing carbon dioxide emissions. So I would argue that in general, you know, I would say sure, we're obviously, you know, over time people have generated sources of carbon, they've also absorbed them, and you can see on the Earth most things are pretty balanced. So you look at, you know, carbon dioxide coming out of solution and going into solution on the water, it's actually in balance. So you see these two arrows are pretty much in balance. Same thing with plant respiration and photosynthesis. These two arrows are balanced as well. But the one arrow that's not balanced, of course, is from fossil fuels. And so this is why I believe that we need to look at plants and algae and look at how they actually are able to reduce CO2 so that we can actually solve some of these emission problems in our world today. This is actually a coal-fired power plant in Missouri. In Labadie, Missouri, this is Ameren's biggest power plant. So you can see that it's all hazy out there, and also there's lots of emissions going out there. So I think it's a viable, you know, it's a viable problem to look at, this reducing CO2 emissions. So if we look at our inspiration from nature, of course we have here the Calvin cycle. So you see carbon dioxide comes in, of course it normally gets fixed by these enzymes, and it's able to make sugars, etc. So this kind of goes around the cycle. Works pretty well. In industrial processes, you're probably not going to be able to scale up these enzymes to large quantities, so you might want to look at all, you know, other types of catalysts to reduce CO2. And so the ultimate goal would be to maybe use sunlight as your source. So instead of enzymes, using sunlight to reduce carbon dioxide, maybe just something useful like methane or methanol or ethanol or some useful chemical. And another side product maybe would be to reduce, split water into making hydrogen gas. So, you know, using sunlight to actually power all of these conversion processes, much like it already does in photosynthetic organisms. Okay. And so I would argue that most, you know, coming as a chemical engineer, when I look at this problem, I realize that most processes people use for CO2 reduction end up producing more CO2 than they actually mitigate it. So it's actually kind of a negative problem here. Okay? And so what we want to do is, of course, look at ways to reduce CO2 photochemically and cleanly. Okay? And so what we've been doing is developing these quantum dynamics models for looking at CO2 photodissociation in the gas phase, but what we're going to do next is to actually extend it to catalytic systems and hopefully, you know, develop a full model of what's going on in this system. And so again, this is the same process you've already seen before. You have carbon dioxide here in the ground state, and you have, you know, incident photon coming in, exciting it to an excited state, right? So same system you've already seen before in photovoltaics. And then what happens, of course, from this excited state is that CO2 would split into CO and O. Okay, so basically what we want to do is model this process. So of course it's still in development, but this is something we aim to do. Same excitation process and then you know, reaction happening. The only difference here is that we're actually calculating a nuclear wave function, so we actually want to look at how, you know, the carbon, you know, CO moiety actually breaks from the oxygen here, so we actually want to know, you know, how the nuclei actually split apart. But essentially, this is what we're doing here in this system. Okay. So, you know, we basically, you know, treat this system as a simple model. Basically, here's, you know, CO2 here. This is OCO. Essentially, just, you know, kind of come up with a simple coordinate system, modeling the distance between the oxygen that breaks off and the center of mass between the CO moiety, and then we just basically have an angle that you know, reflects this. And so you might wonder, well, normally it's a linear molecule. Why do you care about this angle? Well, you know, one thing you might do if you have an excited electron, you know, basically you might go from, you know, let's say like a single state to a triplet state, for instance. So you actually might get some structural changes once you actually have this excitation. So we do actually care about the angle, the OCO angle here. And then we do the same thing with the Schrodinger equation, except this time our Hamiltonian is a little bit more complicated. We have kinetic energy terms, angular momentum terms, because of our angle, orbital angular momentum, same potential energy that we had before. It gets a little bit more complicated this time, just having more terms that we have to just program into our simulation. But this is the term that we actually think is really, really intriguing, this potential energy term. For a gas-based molecule, just CO2, whatever. But if you have a photocatalyst like TiO2 or whatnot, you just basically have to just add the extra potential energy from the catalyst. Okay, so basically you can just extend this model to study reactions on surfaces and other things like that. So looking at TiO2 catalyzed CO2 reduction, etc. So just basically just by modulating this potential energy term, we'd be able to figure out how the CO2 molecule will break. So these are just some of our preliminary results. Of course, this looks kind of weird. This is just one of the wave functions we've been able to calculate. Let me just show you something that's a little bit more interesting. This is actually a probability density for where our atoms essentially are. So right now, you see there's a sort of a little gap between them that might represent the gap between CO and O, for instance. Of course, we still need to refine these, but by doing these full dynamic simulations, you can actually see, basically how our CO2 molecule would actually dissociate over time. Looking at angles, etc. And ultimately, we'd love to kind of model the same process when it's absorbed onto an oxide surface, either ceria or titania, whatnot. So basically, extending this model and looking at real photocatalytic reactions there. So here I would argue that you can use solar energy in lots of different ways to make electricity, but also to make fields. And I think ultimately this is going to be really important. I think for our environment. Okay. So just to summarize these research results here, I would argue that only solar energy really has the potential to satisfy both our current and our projected energy needs. Solar photovoltaics, such as silicon solar cells, have been pretty well studied, but I think there's still a lot of improvement to be made in terms of cost and efficiencies to make them really viable on a really large scale. Solar thermoelectrics, I would say, are promising, but I would say right now they're still kind of in development, efficiencies are still pretty low, but it'd be useful to maybe combine a thermoelectric with a photovoltaic and utilize as much of the solar spectrum as possible. And ultimately, I would say that if we can actually solve this CO2 reduction problem and actually make useful fuels out of this, it might be easiest to actually kind of put efforts into this area and make these fuels that can actually be used for transportation and just our daily energy infrastructure. So I think that would probably be the most viable ultimately, just because chemical fuels have been optimized by nature to store lots of energy and just be used for a long time here. So I want to give a little plug for our outreach activities that we've been doing this semester as part of PARC and also with the Gephardt Institute. We're doing one activity at KIPP Inspiring Academy in Soulard. So we're helping these middle school students from 6th and 7th grade to prepare for a science Olympiad competition. It's the first time they've ever participated. For these students, in a sort of predominantly minority population, most of them are qualified for free lunch. It's a pretty underserved population, but we want them to prepare for a major scientific competition and to do well and to compete well against other schools in the region. So we have about 5 of our WashU students that I'm helping out somewhat to helping out with the staff at KIPP to just learn about different activities. Some of the ones that are most relevant to us, maybe the dynamic planet, for instance, keep the heat. That's what I'm doing. So I'm helping them design an insulating device that will help keep a beaker of water warm for an hour or something. So all the heat transfer and thermo that we learn, I teach WashU students in undergrad, basically I'm teaching these middle school students simplified, no differential equations here, and optics there. And also the other one we've been doing is at Brittany Woods Middle School here in U-City. So we've established a weekly science club called MySpace My World. Everyone still thinks it's something to do with computers for some reason. But we've been developing some different modules that we've been teaching them every week. One thing we realized when we first spoke to them is that they kind of equated science with science fiction. So they kept thinking MySpace was all about aliens with green horns or whatever. But so we've been teaching them essentially like how electricity is made, how wind power works, biomass conversion, and we'll ultimately teach them how to make their own solar cells as well. So there's a lot of activities going on. Hopefully some of you will also be interested in these and want to help out with that. And so with this, I'll just end by thanking my group who's done a lot of research, made things happen. All I had to do was come up with ideas and they actually made it all work. Funding from DOE, from PARC, Photosynthetic Antenna Research Center, Consortium for Clean Coal Utilization, 3M, Washington Olin Fellowship for my student Maria, and also the PARC Institute for funding the outreach activity, and our supercomputing time from NSF Heritage. And with that, I'll conclude and just thank you all for your time and attention. Anyone have any questions?
In China, when you're showing all those devices on the roofs,
Yeah.
how do they haven't addressed storage at all, or is it just, do they even store it?
They just use the heat up water. So basically,
Okay.
In Hong Kong and China, they usually just use the heat up water. And so and so every time you're next to your water heater, you basically have this on-off switch. That basically, when you want to heat it up, you just press it on, and then within a few minutes, it actually heats up pretty well. So they essentially don't need to store. They just heat it as they need it.
Okay.
Yeah. Mhm.
Are there any experimental values of CT available for the system we just mentioned?
For screwdrivers, they have, no one has done it for these gold and silvers. We're actually the first group to actually do gold and silver. Most people have been just focusing on these lanthanum systems, like the very, very huge atoms, like lanthanum and barium, because they're just the biggest ones. They really want to lower this thermal conductivity. And so there's some experimental data for that, and ours are actually pretty close within the values that we've estimated. So for our lanthanum film, we actually have pretty close values, but for silver and gold, there's no experimental data available for it. So I actually just came back from a trip to 3M because they're my sponsors, and I just told them about these results, and they're pretty excited. So hopefully, they actually said they would be interested in fabricating some of these devices and getting some experimental data that would hopefully validate our predictions.